0.14, is that it?
Yeah.
Okay. Now, just 0.59 below him. He succeeds. And an item 0.59 logits below him. 0.59 logits below him is 0.66, was that it?
Yeah, I'll say the higher one was 0.16, no,
0.16 down here. The variance, you're saying? Oh. Now we need to know the success. 0.59 logits below. 0.65. Thank you. All right. And so if you're wondering, and now it's 0.65 times 0.35 as the variance, which comes out at 0.59 logits. What's on the variance side? 0.59. 0.23. All right. Again, we can see why computers are better at this than we are. Let me keep going here. All right, now we're 0.41 above. So 0 is what he made. 0.41 is what we observed. We square that. No, let's say no, 0.41 is the logit difference, not the. What do we expect him to make? 0.41 logits above him. He must be less than a half.
0.40.
Oh, it's pretty fine. 0.40, and the variance is 0.41. 0.24. Okay, and then the last one here, 1.4. Let's see if it goes 0. All right, for an item of 1.41 logits above him, hard for him. So that's going to be
0.16.
0.16. Okay. Squared over 0.16 times 0.84, which is, this is the 1.41 logits on the variance side. 0.16. All right. Now this is where
Okay, I'm almost there.
you're almost there. So that would be 0.93 squared over 0.06 times 0.17 squared over 0.16 times 0.35 squared over 0.23 plus 0.4 0.40 squared over 0.24 times 0.84 squared over 0.16. And what's all that equal?
20.206.
20.21. Is that close? All right. And now we need to divide this by the number of, did I get the right number of terms? 1, 2, 3, 4, 5. That's the length of the test. 5. And that gives an output mean square.
4.04.
4.04. We can see where the mean comes from, because the mean means the average. So when we divide this by 5, we're getting an average. We can see there are squares here. And so this means we've got an output mean square with a value 4. Or looked at from another point of view, we could say this is essentially a chi-square statistic with value of 20 and 5 degrees of freedom here, because we've got 5 separate observations, so that the probability of observing this is the same thing as observing a chi-square value of 20 with 5 degrees of freedom, which of course is very, very unlikely to be observed. And its size, average size, is 4, and as we discovered before, its expectation is 1, so this indicates a very unexpected pattern, very noisy. We'll contrast this with Mary. Fortunately with Mary, all that's changed with Mary, the variances stay the same, the expectations stay the same, all that's changed is the data values. So we can put in for Mary the changed data values. 0.06 and 0.83 squared over 0.16 plus 0.65 squared over 0.23 plus 0.4 squared over 0.24 plus 0.16 squared over 0.16 Is that right? Approximately? All right. So now, our determined calculator, in fact, back in the 1930s, if you said I had my calculator do this, you'd actually mean a person. Back in the 1930s, people were called calculators. It wasn't machines that were called calculators, it was people who were called calculators. Right. Let's see what this produces here. Let's see, that was, I've got this wrong. That was, let's see, that was George. So this is Mary here, which is, they both got the same ability.
1.623.
1.62, is this after the division or before the division?
Before the division.
1.623, and then we're going to divide this. This is the sum of all these individual terms. And when we divide this by 5, we get
0.325.
0.325, something like that. All right, we now see that this value is now well below 1, meaning that this is a very predictable piece of data. In fact, we can see Mary's response string goes 1, 1, 1, 0, 0. So in fact, it's following what's called the Gutman pattern, where she's succeeding on everything easy, failing on everything hard. And if we observed this over a much longer string of items, what would happen would be this mean square would go lower and lower and lower, meaning this data is becoming more and more predictable. And at some point we'll begin to think, is there something forcing this pattern to occur? For instance, this may be an arithmetic test that's being given in item difficulty order, as some intelligence tests, things like that are, that beginning test. And what happened was that this person worked slowly and steadily through all the items, getting them all right, until, say, time ran out. And then, under many scoring rules, when the test stopped for whatever reason, all the items you haven't got to yet automatically get marked wrong, in which case Mary would have succeeded on all the easy items, time ran out, she gets wrong answers imputed to all the hard items, and she ends up with a very predictable set of data. But the reason it's predictable is because something else is constraining that way, namely the clock. So this is the outfit statistic. We can see it's computed one observation at a time, and what would happen would be is that if there is one very unexpected response, for instance, down here, what have we got down here? Let's look at George's unexpected failure on an easy item. What is this in fact? It's 0.93.
14.42.
Okay, 14 point, well, just see, it's 0.93 times 0.93 over 0.06. All right, that's just about 0.9 times 0.9. That's about what's 0.93 times 0.93?
0.86.
0.86. So that's 0.86 times 0.0 divided by 0.06, which is, we just mentioned to you,
14.42.
14.42. Now, if you remember that the final result for George was 20, and we see that 14 of that 20 just came from this very first term. So what this means is that outfit statistic, this statistic here, is very sensitive to unusual, odd responses. So one failure on an easy item produces a very big value for that particular item, which means that the entire sum for the outfit statistic can get very large. So, for the outfit statistic is very sensitive to individual unexpected responses, unexpected failures, or unexpected successes. Even though, maybe without that response, the rest of his response string may make sense. So maybe if we disregarded this response, the rest of what he did would make sense, would be explicable, would be not that unexpected. This one response has made the outfit look really bad, look a disaster, look like fall. So as this was particularly a concern 20, 30 years ago with multiple choice tests, where maybe a careless mistake or a lucky guess would make it look like the entire response pattern was in chaos, an alternative form of this statistic, the outfit statistic, was devised, which lessened the influence of these extreme values, these extreme outlying observations, and this was the infit statistic. And the infit statistic, which is also called information weighted statistic, takes a different approach. Instead of adding up the terms one at a time in the manner of the outfit statistic, what it does is it adds up all the tops and divides by all the bottoms. Now, we know that the expected value of each of these terms in the outfit statistic is 1. So, if we add up all the tops and divide by all the bottoms, what's their expected value? We've got 5 terms here. The expected value of each term is 1. If we take the tops of all those terms, add them up, and the bottoms, the numerators and the denominators, add them up, what's the expected value when we divide the sum of all the tops by the sum of all the bottoms? Yeah, it's still 1. All right. You can do a little arithmetic yourself if you're not convinced. But what that means then is if we take the sum of all the x minus e squareds on the top and the sum of all the variances on the bottom, we expect to have a value close to 1. But what will have happened will be any individual unexpected right or wrong will get added in with all the rest instead of featuring on its own, as happens with the outfit statistic. So let's calculate the infit statistic for George and see how it looks different. Okay, so if we open 0 minus 0.93 squared, adding up all the tops, 1 minus 0.83 squared plus 1 minus 0.65 squared plus 0 minus 0.40 squared plus 1 minus 0.6 squared. So that's all the tops. And then we divide it by the sum of all the bottoms, which is 0.06 plus 0.16 plus 0.23 plus 0.24 plus 0.16. All right. Brave individual. Have you got the top or the bottom?
The top is 1.882.
1.882. And the bottom is? Okay, so when we divide 0.8, 0.85, when we divide 0.882 by 0.85,
2.21.
2.21. Okay. We can see now that the infit statistic, which has actually got exactly the same numbers in it, is now downweighting the influence of this extreme outlier here. And the resulting mean square is now only half the size of the outfit. The infit's only half the size of the outfit. So it's lessening the influence of this extreme observation. And consequently, we could say, if we want to look at it from the other perspective, we could say it's increasing the influence of the observations that aren't extreme. In other words, the more central observations. So another way of thinking about the outfit and infit is the outfit is the outlier sensitive version of the statistic, and the infit is more sensitive to the inliers, the observations that are more closely targeted on the person. Now, with a short instrument test like this, we don't get the entire flavor of what's going on here. But the way these summations work in the infit is that the information piles up around the person because of the way that these summations work. And if there is an unusual pattern near the person, the in-fit statistic is more likely to notice it. For instance, if we have traditional addition, subtraction, multiplication, division, if we happen to encounter somebody in our sample that succeeds on the addition, fails on subtraction, succeeds on multiplication, and fails on division, then from the outfit point of view, the failure on division and the success on addition are as predicted. From the in-fit statistics point of view, it is the pattern of failure on subtraction and success on multiplication, assuming multiplication to be more difficult than subtraction, that's unexpected. It's not any individual observation that's unexpected, it's the entire pattern. This makes outfit statistic much easier to interpret because we're usually looking for just strange responses, lucky guesses, careless mistakes, misreadings, miskeyings, miscodings, whatever it is. Somebody on the attitude survey that didn't notice the word not in the rating scale item, so went way off to the wrong end of the scale. But in-fit is usually much harder to diagnose because it usually involves a pattern of behavior, and we can't just look at a particular response and say, oh, that's it. We usually have to end up looking at a pattern of things, and sometimes the patterns are just too obscure to work out what's going on because they may relate to some very personal aspect of the individual or some hidden feature of the item that is difficult to detect. So this is the in-fit statistic, and that's the outfit. To summarize this into a couple of pictures, we could say that we have a set of items. The outfit statistic is more sensitive at the ends of the test, the parts of the test away from the person, and the in-fit statistic is more sensitive to the area of the test closer to the person, and less sensitive to those away from the person. If we're dealing, though, with rating scales with long scales, like a typical Likert scale, maybe I strongly disagree, maybe there's a neutral, maybe there isn't, agree, strongly agree, often the width of the scale is so wide that it's much wider than the sample of the people to go from all the range of attitude from one end to the other. In that case, all that we ever see in the data is maybe the range from here to here. If that's the case, then in-fit and outfit are just about telling us the same story. So if you look at your results and you see that in-fit and outfit statistics are about the same value, what that means is that everything is, relatively speaking, so central that we're not able to see in these particular data the differences between the statistics which are out of the tail. In that case, if they're both reporting the same value, it really doesn't matter which of the two you use, because they are the same value. And, outfit is the one that's closer to the traditional statistical approach to things, and so referees of papers and things like that may be more comfortable with an explanation of outfit than of in-fit, because in-fit introduces this, what they would call information weighting, and then they say, well, why do you use a weighted statistic when an unweighted one gives the same results? So I would go with outfit under those circumstances. So that's a quick look at computing in-fit and outfit for our odd friend George, and you can do the same thing for Mary to see what happens. We discovered that both in-fit and outfit are predicting, in other words, our values less than 1 for Mary, because she is exhibiting predictable behavior both close to herself and also far away. Thank you.
I got that. Do people have questions?
And that's
I was saying at the beginning that nobody used the blackboard in a while, and I was mentioning, probably it's because my old ways of doing things, but this gives me time to breathe and think and absorb it, so I really like that.
you don't think it would work so well if I'd done it in PowerPoint.
No.
Click, 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 click.
No.
I mean, while he's erasing, do the
Yeah,
next one, you
yeah,
absorb what
yeah.
you can.
It must be because of so old fashioned. Not that Everett's slides are not nice, but.
Well, I had the complaint early on that when I used to do this kind of stuff,
Oh, this is beautiful.
they didn't have anything, I went too fast, so they didn't have anything to take notes on, so I started giving overheads
Mhm.
out of all my lecture notes.
Yeah.
Now I get the opposite. It's like,
No.
You can never please it.
no, he can't win.
Yes.
With the infit statistics, in the readings, I'm under the impression that if you're evaluating dichotomous items on an assessment or a test or something, in looking at those items that measure what you think they're measuring, the infit statistic tends to tell you if they're measuring something different than what you're measuring, or more around unidimensionality. And the outfit statistics are those things that pick up guessing patterns and things like that.
Well, that's true, because if the outfit statistic is usually very easily diagnosed and often ties down to individuals, like individuals with strange behavior. They're doing something unusual. If the infit is got a large value, that means something's going on with the people for whom the item is supposed to work, and that's much more problematic because then usually you don't understand. It's like what I was illustrating there, sometimes called alternative curriculum, with the addition of somebody who learns multiplication before subtraction. But then you don't know what to do about that item. It's so. Even if you can diagnose the problem, say, oh, well, the reason is, a third of the sample learn multiplication before subtraction. Okay, now how are we going to measure those people? That's a problem. So if one can discover items where that doesn't occur, one propose them. Yes?
I have a question. I mean, it's something I probably will have to explore on my own, but couldn't you group, because you can get those patterns of unexpected responses. If you wanted to, couldn't you group the individuals into groups based on those unexpected patterns and then go back and reanalyze them as groups and just kind of see, I'm thinking specifically like from a healthcare situation, because those unexpected patterns of responses might be pretty critical in what you're looking for. And it might actually take care of some of the problems that you're seeing. You think that?
Definitely, yeah. Different. I know when I was working with the Rehab Foundation on patients, for instance, burn patients, turned out to have quite a different profile than the other patients we were dealing with. And that's where in Winsteps, for instance, the principal components analysis of residuals. This what we were doing here was we were summing residuals. But what you're talking about is looking for patterns within the residuals.
Right.
And in Winsteps, there's a principal components analysis of them, which is doing exactly what you're saying. We look for response strings that are correlated with each other, but correlated against or uncorrelated with, counter-correlated with everything else. And we'd say, oh, well, this is a separate group, whether it's items or people, that have got a different profile. And that would be good if you discovered a group. Maybe, for instance, in a language test, it might be a group of people who've got English as a second language. Or in a clinical setting, it might be people with, say, left brain versus right brain dysfunction. And say, oh, well, we can now divide the group in two. And the decision often is, as it was with us with burn patients, is this a big enough group to set up an entire separate measurement system for? Well, they decided with burn patients, there's just not. There's just not enough of them that go through the Rehabilitation Institute of Chicago to set up a whole separate system. But we knew that they wouldn't fit with the overall system, but just had to live with that.
So technically, like if you knew like a priori, like you had two languages, say like it's German and French, whatever, and then you notice like responses where you had mostly women responding in certain ways or men, and you could go back and just do German, women, French.
Yeah.
So just go back.
In fact, what Carl Granger does in Buffalo, this is with patients with back problems, he has detected several different types of back problem, and the items for each of them have, as it were, a separate measuring instrument. And when the person comes into his consulting room, They take the instrument, and then he sees which of the several different item hierarchies their responses fit with best, and uses that to diagnose what sort of back problem they've got. So you could do the same thing in your situation. Somebody comes in, you're not quite sure what their linguistic background is, for instance. You could have them take the test and then say, well, which linguistic background does their response string fit with best? And that might help us put them into the correct language training situation, for instance. Oh.
I have a question. I know that ideally your mean square, your outfit, your infit statistic should be 1 and can range from 0 to infinity.
Yeah.
And there are guidelines in terms of what is conventionally acceptable. Is there a good way to come up with a rationale? Because when people say, what makes that right? Makes these cutoffs right? Why do you use this criteria? I'm trying to come up with a rationale that would be based on a substantive theory, like I can tolerate this much error. And is there some way we can tie those things together?
Well, definitely. I mean, there's a mathematical solution. Basically, as I was mentioning, the range, the expected value is 1, and the range goes from 0 up to infinity. This is for the size. Now, statisticians tend to like to look for the improbability of something, in which case they would take the, we could say, the significance of this. But the problem with things like taking the significance or the improbability of something is that as the sample size gets larger, everything becomes more improbable. And the result is, before long, you discover everything is improbable. And that even a value of 1.1 on a mean square, if you've got a large enough sample size, is significantly different from 1, even though its substantive impact is nothing. But what is a substantive impact? Well, there are key values are 1.5 for the mean squares and 2. In doing simulations and looking at real data, what happens is, at 1.0, the amount of variation in the data matches what is predicted for the data. When it's got up to 1.5, we've now got 50% extra variation. So we've now introduced 50% extra noise. What happens when we get to this point is that this data is now not contributing towards the measurement system, constructed measurement system, but it's not degrading it either. When we get to the value of 2.0, now there is as much unexplained variance in the data as there is expected data, predicted variance. Now it's like we're listening to a record, an old LP sort of record. Here we get hearing the music with maybe just a light background hum, which used to be traditional, everything hummed back in those days. Here we're going to get a few scratches. Here now the background noise on the record is starting to overwhelm the music. And so once we get about here, there's more noise than there is useful information, and so this starts to degrade the measurement process. Now sometimes when we go back and look at these, we discover this degradation is just due to 1 or 2 responses. But what that means is there are 1 or 2 responses that are contradicting all the rest of them to such an extent that it's like a crack in the record, we could say. It's really ruining the music. If we can deal with the crack by removing those responses, often it hardly changes the actual music at all. If you're listening to an old 78 or something like that, you hear the crack very clearly, but if you take the crack out, it hardly changes the tune at all. And that's what tends to happen here. Often these large mean squares look alarming, but then when you deal with them by saying, well, let's pretend that particular observation point wasn't observed, we'll just mark it missing data. What actual impact has it had on the measurement system? What changes it make? Often the change is so small as to be unnoticeable. So, but there are key levels at 1.5 and 2. Going the other way, it seems to be something like around 0.3 or something. In other words, this means when you've got down to here, this item or this person is only acting like a third of a person or a third of an item. Seems to be some value like that. When you get a value less than about 0.3, what it's saying now is that this data is becoming so predictable we need to bother to collect it, because we know what it means. Now that doesn't mean that it's bad. In fact, it might mean that it's very good. But it means that as far as constructing measures, it's not really helping us build the measurement system. It's affirming the measurement system, but it's not helping us build it. Does that help? That's some thoughts. And Rasch measurement transactions, of course, on our favorite website, www.rasch.org/RMT, has lots of research notes discussing this type of situation from all sorts of different angles, going back a large number of years.